Hello, this is classwork for Math 2-3. This is page 10, problem number 1 concerning power models. Looking at page 10, at the top, investigation 2 talks about power models. We're going to talk about common forms of direct and inverse variation that we've already seen, and then extend the idea to other kinds of rules that are in the form of this right here and this right here. Because these models have a power in them, they are raised to some power, in this case r, where r could be any number like 2, 3, or 4. These are called power models or power functions. Most direct variation looks something like this. Y equals k times x, where k is some constant value. It's any number. We've seen plenty of examples of this. Here's an example. As the weight of a bungee jumper goes up, not as one bungee jumper gets more heavy, but as you put heavier and heavier people on a bungee cord, the cord stretches according to an equation. C, the length of the cord, equals 0.2 times the weight of the jumper. In other words, for every pound that the weight of the jumper increases, as you put bigger and bigger people on it, the cord is going to stretch 0.2 feet. That is direct variation. As W increases, C, the length of the cord, also increases, and it fits the form of the equation y equals kx. One variable can vary directly with the power of another variable also. And when we say power, we mean like squared or cubed or to the fourth power. Here's an example. As the length of the side of a square increases, the area increases by the square of s. And square, as you know, is raised to the second power. So here's a square where the side length is s, the square is about this big, and we would calculate the area by the equation s squared. This fits the form of the equation because there's a constant proportionality of 1, you just don't see it. So in this case, k equals 1, and instead of a y equals kx, we've got a equals k, which is 1, a equals s raised to the second power, or squared. And here you can see with a bigger square, s is a bigger number, so the area of the whole square is bigger now. And the area is calculated still by s squared. So it's direct variation, but with a power function. It works the same for inverse variation that we're familiar with. Most inverse, that should say inverse. Most inverse variation looks like this. Y equals k divided by x instead of times, or y equals k over x, where k, again, is some constant of proportionality. This can also have a power. Just like the direct variation, we could have y equals 3 divided by x squared, or b equals 0.07 over t cubed, which is t raised to the third power. This can be used in the real world to model certain functions. In this case, we're looking for the intensity of sound or light. Intensity, of course, is how strong something is. The intensity of sound from a voice, or like from these guys, from their band, the intensity of sound from a voice or of a light from a flashlight is related to the distance from the source to the receiving ear or surface. In other words, the closer you are to music, to the speakers, the louder it is, and the farther away you get, the less loud it is. Same with light from a flashlight. The closer you are to it, the brighter it's going to be, and the farther away from it you get, the less bright it's going to be. Looking at these graphs, we're now on page 10, problem number 1, down at the bottom. A asks us to describe the patterns of change here. Here in graph 1, this one looks like as the distance, which is along the x-axis, as the distance is low, as you're close to the object, both light and sound are going to start strong, drop off sharply as you get away, and then gradually kind of flatten out near zero here. Notice, though, that it never touches zero. This one would be if, as the distance from the source gets higher, the intensity of the sound or the light is going to drop at a constant rate. As you move away from the source, it's going to drop at a constant rate and eventually get down here and touch zero. In this third one, as you move away from the source, the intensity gradually drops off until you're farther away, and then it sharply drops off at the end, going down to zero. We're going to try and figure out with a little investigation which one of these seems to be the most like the real situation. We'll come back to these three graphs when you're working on problem 2. So, now that my speaking part is done, in your groups, use the worksheet that I've given you to complete problem number 2 that starts on page 11 and continues onto page 12. If you finish early, here's the homework assignment. Homework tonight, this is due Monday, December 2nd. That's the day we get back from the Thanksgiving time off. That's because that's the next blue day, because Lewiston and Auburn have school tomorrow on Wednesday the 27th, the day before Thanksgiving, which here in Poland we have the day off. So because of our relationship with the LRTC, tomorrow counts as a silver day, but we don't go to school on it. So Monday, when we get back, this homework is due. The homework due Monday, December 2nd. The meets is page 18, number 5. The exceeds is page 22, number 16. Or you can still get a 4 on the assignment, but you can also get closer to honors challenge credit for the semester if you do the honors challenge problem on page 23, problem number 20. Remember, do the exceeds or the honors challenge to get a 4 on the assignment, not both. Also notice with the meets, there's no review problem this time. It's just page 18, problem number 5. Now go to work.